Hello everyone and welcome to this third episode of our series presenting DIAMBRA, our dueling AI arena. So I'm glad to be here today again this new week after last one, and I see that we are already active in chat. Hello everyone, hello Lord Morgul, hello Erchimau. I'm really happy to have you here with me again. And the main topic of today live session will be reveal of the third game. Hello Buele, super glad to have you here also. And so yes, the main topic is the reveal of the third game. We interfaced it in our platform, and it's a kind of cool game. And hello the Rocker Man, hello, glad to have you here also today. Please, as in the last episode, please be active in the chat. Don't hesitate to ask questions, cool things you may be interested in. And so, as I was saying, today we are gonna see a new game. It's a cool one. I'm almost sure you all know it. It has been not so easy to integrate this one. I will tell you more about it later. But before diving into this new game, let me do a brief recap of last episodes. In particular, last week we had two different episodes, the launch and the second one. And these two episodes we showed the first and the second game interfaced. The first one is Dead or Alive++, and the second one is Street Fighter 3. If you miss the live events, you can always find them in the dedicated channel. In particular, in YouTube, you can find a direct link to the playlist in our website, diambra.artificialtwin.com. Here you can go directly into the playlist, and so you can find all events here to follow. So yeah, you can go there because we already thought a little bit about how this entire thing works. So you can find additional information there, how the live events are organized. You can see there, you can find there random agents playing in those games. If you want to have, let's say, an idea of or a comparison with let's say what's the baseline, the typical baseline that is used to evaluate how a reinforcement learning agent is learning. It's a standard way to compare and to understand if that specific agent is learning something with respect to a common baseline, that is the random agent. So before moving to the reveal of this new game, I would like to share with you a few information about, let's say, details about few important things that are important to keep in mind when approaching these fields. In particular, let me show you few information, let's say a few images. This one, you already saw it in the very first live, I think. And this is the one screenshot of OpenAI Five finals. Basically, OpenAI was able to train their own reinforcement learning algorithm to play Dota 2, and they were super performant in the sense that they were able to beat world champions in a 5 versus 5 match. So this is a screenshot taken in that occasion, and this image is here because one of the typical questions that are posed when we talk about reinforcement learning in video games is how complex can be the video game to be approached with these techniques. Well, OpenAI 5 is one example. We do have also other examples in this field, in particular DeepMind solving, let's say, Go, the game of Go, as well as StarCraft. What's the point here? Yeah, the key point is these games are really complex. Really complex it means that they have quite a huge observation space. It's called the observation space is basically the entire configuration possible of the game that you are allowed to access. So basically it is the set of different states in which the game can be that you are able to sense. So in a fighting game, as the ones that we are seeing in our episodes, the state of the game is represented by, in some sense, the frame that you are presented with, but also information about like health of the characters, position of the characters, time remaining, these kind of things that are the details needed to understand where you are, how the game is proceeding. In games like Dota 2, for example, you do have a huge space of describing the state of your game. So it in this sense is way more complex. At the same time, also the set of actions you are allowed to take and among which you have to choose is way bigger. In our case, you can perform move actions, attack actions, and as we already did in our previous episodes, you can basically list them all. They are in the range of 10 to 20 actions. So yes, this is more or less our range in this type of games. In this type of games like Dota 2, well, the space of actions is way bigger. And we will see that these two aspects are of primary importance when you have to evaluate what's the challenge in training an RL algorithm to tackle these games. So as I was saying, yes, apart from Dota, DeepMind in 2017 was able to basically solve the game of Go, meaning that they were able to beat the world champion with a complex algorithm trained with RL techniques. They started with AlphaGo, then they improved their version and obtaining a new version called AlphaGo Zero, and then they obtained an improved one called AlphaZero that basically is more or less a generalization of AlphaGo Zero that is applicable also on chess and other games. But basically they built this algorithm that were able to tackle the great complexity of this game. This picture is here just to convey you the idea of all possible, let's say, how big is the space of possible configuration in this game. Basically every board configuration can result in a huge amount of configuration depending on the action you choose. And so it's really a challenging task to be able to understand every possible, let's say, configuration and react to it. Thank you, Lord, for your question. Actually, Discord channel is in our plans, and we will be sharing it soon as soon as we think it's the right time. So more on this later on in our episodes. Thank you for asking. So one key point about AlphaGo and AlphaGo Zero in particular is the fact that they moved from using human experience in the first one to avoiding using human experience in AlphaGo Zero, meaning that AlphaGo Zero was able to learn how to play this game just starting from knowing the rules. No usage of human experience, and basically implementing the so-called self-play. Self-play is a super cool technique in the field of reinforcement learning that is basically something that allows you to play on both sides, in this case, in the case of Go, on both sides of the board, and you basically play against yourself. This means that you are able to generate a huge amount of data. This is not the case when you need to train yourself using human experience. You do have to collect the experience by humans. In case of using self-play, this is not needed, since you generate all these games on the fly, playing against yourself. And this is also an additional huge advantage, and this is basically the fact that you are playing against an opponent that is more or less on the same level of yourself. This gives birth of to, let's say, really games that are really similar, and also in which the opponents are on the same level, and so they are challenging someone that is able to playing on the same level. And so this speeds up training, and it's a key technique for advanced problems in reinforcement learning. So moving to Dota 2, it is useful to have an idea of how complex the game is. So this is a brief description. You can find it in OpenAI blog, and it gives you an idea of how complex this type of game is. So first of all, it's a long time horizon problem. In fact, the game runs at 30 frames per second on an average of 45 minutes. It means that there are 80,000 steps, ticks per game. And so this gives you the idea of how long is the horizon in which you have to collect this reward from the environment and understand how your action impacted on the situation that is in the game. We have a question from the chat. Mao is asking, you mean the more complex is the game in terms of graphics and parameters, the more difficult is the configuration of the agent, and the more is the computational power required? Yes, of course, you are right. So it depends on how complex is the game, and also it is also related with how far in time your action will have effect, and also in some sense how back in time you have to go to identify the key action that allowed you to reach a good position in the game. Lord Morgul is saying that it's needed optimization in the sense of hardware. Of course, optimization is a key point. We are gonna see a really interesting scheme from OpenAI describing their architecture. And that architecture will be super interesting to take a look at. Lord Morgul is saying take as an example, converted game basic hardware is easy to manage. Yes, in some sense, managing hardware is a really complex thing. Also, because you do have to parallelize execution of your game that is interfaced with your reinforcement learning algorithm, meaning that you don't need only one instance, so one game going on. You need to have multiple instances of the same game going on in parallel, and you have to gather information from all those instances at the same time and using in parallel those information, those elements to train your algorithm. So another key point is the fact that the state in Dota 2 is partially observable, meaning that you don't have access to some game state. For example, units and buildings can only see the area around them, and the rest of the map is covered in a fog, hiding enemies and their strategies. So this is important because this, as I was saying, is basically the configuration called partially observable, and so it's you don't have access to every information, to every detail that is inside your game state. Then another key point in Dota 2 is the high-dimensional continuous action space. So you can choose actions, and basically some of them are continuous actions. For example, coordinates of your mouse click can vary continuously in a range, and so taking into account all these possible alternatives, you have an average of around 1,000 valid actions in each game step. Just to have an idea, and for comparison, the average number of actions in chess and in Go is 35 and 250 respectively. So this gives you an idea of how complex is the action space. Of course, and the last point speaks about the complex high-dimensional continuous observation space. The game is played on a large continuous map. It contains, in the 5 versus 5 mode, 10 areas, dozen of buildings, and so you do have a huge observation space. And as you can see in the case of OpenAI 5, the parameters that you need to take into account, that are mostly floating point values, is around 20,000. So 20,000 numbers, and they represent basically all information a human is allowed to access. So, okay, we understood in these cases that are more or less state-of-the-art, current state-of-the-art for reinforcement learning. In the context, they needed to tackle this high-dimensional action and observation space, long time horizon, and partially observable states. To tackle this problem, I can show you here OpenAI 5 how it was working on what kind of hardware it has been trained. And so, as you can read here, we do have 128,000 CPUs. We had 256 P100 GPUs, and so basically running in this mode, you see you have basically every day 180 years of experience collected. So the system was playing the equivalent of 180 years every day of experience of a common human player. So you see, you have the idea of how big needs to be your infrastructure when you want to tackle these problems with reinforcement learning. In fact, one key roadblock, current roadblock of reinforcement learning in the field in general, the applicability of it is the so-called sample inefficiency, meaning that in order to apply it, you do have to use a huge amount of samples, a huge amount of experience. You have to run your games, your environments for really a long time. And the next picture shows you the architecture of OpenAI solution. So first of all, in the upper part, we have the training, let's say the training subset of instances and hardware. In the lower part, we have the architecture dedicated only to evaluation of the current version of the algorithm. In fact, if you want to understand if your algorithm is learning something, you have to evaluate it. So as you can see here, they made their algorithm play against, for example, hard-coded scripted bot, previous similar bot, and against himself, allowing human to watch and evaluate how he was behaving. So only, take this into account, only for evaluation purposes, it was using 2,500 CPUs only for evaluation. For training, as you can see on the upper part, there were 500 CPUs for executing the environment, so collecting samples from the environment, and they were running their episodes 80% against their current bot and 20% against mixtures of past versions. They were using randomized game settings and pushing data every 60 seconds of gameplay. And so using discounted rewards in these 60 seconds. Now, these data samples are collected and sent to the optimizers. As you can see, this configuration is repeated for every one of all 256 optimizers, all those P100 GPUs, and they were using, as a reinforcement learning algorithm, they were using proximal policy optimization with Adam, batches of approximately 4,000 observation, and you see here that this was basically run in parallel with all 256 GPUs. So basically this was their architecture, and all this training loop was to basically define those model parameters. Those are the parameters describing the logic behind how their model was choosing actions given an observation. These model parameters are, as you can read here, approximately 10 million floats. Okay, so here is where all the learning happens and all the knowledge is stored. So this is the architecture of OpenAI 5. Now, as you can imagine, this kind of infrastructure requires quite a lot of money to build and to run. I just read an estimation of how was worth it the infrastructure for AlphaGo Zero, and its value was around $25 million. So just to manage that specific infrastructure and to run their training on that specific hardware resources. So it's clear that currently there is quite a huge bottleneck in terms of computing power required to train this algorithm, this type of technology on problems of this type of sites. Now, our own environments are not so easy, but of course way easier than these ones. They are not so easy because on one side, yes, we have only discrete actions, meaning move actions and attack actions. But our observation space is not so small. In fact, one key point, I mean the most important one of our observation space is the frame, the pixel frame. We are using that as a specific information about the game state. Then we are using additional information that I already showed you in previous episodes. I will go through it really quickly also today. So moving to our environment, you see it here. So this is again our window layout. You should be familiar with it now. And just a quick recap, on the left side we do have our reinforcement learning typical sketch contextualized in DIAMBRA. And so we have our AI agent sending action through the gamepad to the environment, and then receiving in return the state of the game composed by 6 frames, last 6 frames, AI and com health, AI character, previous actions, side of AI and com opponent, meaning if it's on the left or on the right on the screen, and the stage number. This is the typical AI versus com configuration. And apart from the state, we also have the reward that is also the immediate one and the cumulative reward, and they are sent to the AI agent that use them to learn, and then again the cycle restarts. On the right side you see on the upper part the game going on, and in the bottom part you see actions running log of the actions showing live. So let's now move to the reveal of this third game. So bear with me for a second. I will start everything from the terminal, and so here we are. Let's start and let's see what's the third game we are going to see in DIAMBRA. Okay, so this is in some sense it has been quite complex to interface this one. I will tell you why. You will see it. So as you probably understand, you can see it here. So we are talking about Tekken Tag Tournament. So I must say this game has been hard to interface. It's kind of buggy a little bit, and I will now play along with the keyboard just to talk a little bit about it while the game goes on. So as you can see, now it's kind of different with respect to other games. In particular, you can see that we had to choose 2 players, not 1, and they can be interchanged. With the tag button, you can change between them. So this is one of the key differences with respect to the other games. There is actually there are quite a lot of differences in other aspects. One of them is that your health is able to recharge. In fact, you can see Yoshimitsu in the background is recharging his health. Now Jin can do the same thing in background. As you can see, is recharging itself. Now this, of course, is something really different with respect to the other games. And now, okay. Andrea Sidis is suggesting moves. I'm really bad at this game. You will see it pretty soon. Now I'm selecting these characters here. I don't know if you have suggestions, because I still do. While I already trained agents in Dead or Alive and in Street Fighter. I do have to train agents in Tekken, and so I was thinking about training Jin and Yoshimitsu, this couple. I don't know if you prefer someone else to be trained on this game, and so let me know. Maybe I can still change it. Now I will play the random agent with these two. So this is another key difference. So health that is recharging in the background on one side, and also the fact that you can interchange between two different characters. So let me stop it here. And let's move now. Let me keep this one in the background while I talk. Now, Andrea, you seem to know it very well. Okay, yeah, you can train yourself on it, and maybe we can try to let you challenge the AI once trained, maybe. Who knows? We have a question from Marco about previous discussion. Could better defined training procedures reduce the computational power required at the moment, or it will be more realistic to wait for reduced cost and enhanced availability of the needed computational power in future? Of course, super good question, Marco. Thank you. The idea, the feeling in the context is that a major breakthrough in theory is needed to cut down the need for computational power. Of course, with the so-called Moore law, and that will allow to access to more computational power with let's say in a more cheaper way will help definitely, but the feeling is that a major breakthrough is needed to make these solutions viable, meaning to the usage of RL to address this kind of problem. So I was speaking about specific aspects for Tekken. First of all, I told you double character selection on one side. You can exchange both characters during the gameplay. This is another difference. The health is recharging while playing, and you will see it also here. You will see that the health of the first character will be going up while playing. Another important difference is that not all characters have the same level of health. Some of them they have let's say a larger health bar, and some of them have a small one. So in this sense, they are not even in terms of the amount of health they have. And so this is another difference that is specific for Tekken. Now it's time to take a look at the random agent playing. Now you will see it will be pretty fast to die. I mean, it will die pretty soon. In fact, we can run even 10 episodes instead of only 5. Now, let me just go to AI versus com. Now we can change this one, and we are playing random versus com. This will help us remembering what we are seeing. Now, let me see. I do have to do one trick because, as I told you, this game is somehow a little bit buggy, and so I do have to do a few tricks. I'm working on it, but I think it won't be a problem when I will distribute these environments. So let's see. I will be using in this one Jin and Yoshimitsu in a random play. Let's see what's the average performance that they will be able to reach. So let's run it. AI versus com. Now let's see. Let's hope it will be go on the right way, because as I told you, it's kind of problematic this game, but still I wanted to implement it because, you know, it's so famous and so characteristic. So now let's see. We are now at the stage of character selection. We see this frame here is just freezed, but you will be seeing the live representation pretty soon. Just a sec. Okay, now you see we have Jin and Yoshimitsu. You will see here level of health that is, you see now it's going up because, and this is let's say a limitation of current representation. In this representation on the left, we are only seeing the first character selected. In our case, we are only see AI health of Jin, not Yoshimitsu one. And this is because we need to still to retrieve from the environment the information about which one of the two characters selected is playing. So we have access to both health of Jin as well as Yoshimitsu at the same time, but here we are representing only health of the first one, so in this case Jin. Now in the first episode we obtained minus 2.14 as cumulative reward for our agent. Now we'll see, but more or less it will be something similar. It will be something similar because, you know, in this game it appears to be pretty complex to obtain a higher reward with a random agent. So we will see how using an RL algorithm will help us in improving this performance. Okay, nice question from Curaro. No, the agent he's asking, his random agent selecting character itself. No, we are in this case we are selecting always Jin and Yoshimitsu. Of course, if you want a single only agent able to play with every possible character in the game, you do need to make him selecting randomly your his characters. So in that case, he needs to basically accumulate experience and test every single character available in the board. Another important difference of this game with respect to the others is the number of characters available. You saw that is basically a ton of characters. Is in the range of 30, I think. Oh, great. So Curaro, okay, Curaro, it's okay. What you? So my answer was correct in that sense. Is selection is scripted. You can specify a number of the name of the character you want to use. You can specify to choose them randomly. You can specify when you are playing with the gamepad to select them using the gamepad. Rockerman, you mean a different thing, and that's important. During a random game, of course, they are changing sides, meaning Jin and Yoshimitsu, they are tagging one the other in a random way. So of course, since the tag button is one of the actions, of course they are performing it randomly. So one thing that the reinforcement learning agent needs to understand is the fact that when your health when the health of the player that is playing is low, it has to press the tag button. So I expect it to understand, to learn this. So basically, I expect the reinforcement learning agent to be able to manage the fact that recharge is allowed in this game. And so yes, we will see. Now we are going to see episode number 4. Now you see, in this case, since we have health recharging and these kind of things, the total cumulative reward, the maximum one, is not limited. I mean, it's not so easy to understand what's the higher limit for the total cumulative reward. Lord Morgul is saying that the agent needs also to learn not only how and when, but also to build a strategy among the, let's say, things like tagging and exchanging characters appropriately. Curaro, great question. Is health recharge rewarded positively? Yes, it is. In fact, basically you will see your health going up, and this will be a positive reward for you. So in this sense, it will be able to understand that is a good thing, and it will be, let's say, prone to favor this solution. So we are gonna see the fifth episode, and at the end we will be presented with the average performance of the random agent. So this is the last episode. I believe that the random agent was not able to go to move to stage 2 in a single episode we just saw. So yeah, it's pretty bad in this sense. I will try to do a run myself, but as you will see, I'm even less proficient at this game with respect to the random agent. Oh, great point about Curaro. He's saying, I think that one of the hardest part to train is counters. Some characters are stronger than others with some others. Yeah, you are right. You know, counter moves and this type of strategies are hard to understand, as well as combo in some sense. Okay, so we ended our row of 5 episodes, and as you can see here, the average reward for the random agent is around minus 2.72, let's say. So pretty bad in some sense, not a single stage passed by the random agent. It will be quite, let's say, easy to understand if our learning agent was able to improve with respect to the random one. Rockerman is asking, does a different game scenario represent a greater difficulty of interpretation for the agent? This is a good point. I'm not sure I got it correctly, but I'll try to answer. Let me know if it was your question was in this regard. We saw so far 3 different games. We saw Dead or Alive, we saw Street Fighter 3, and we saw Tekken. Now, 2 of them, Dead or Alive and Tekken, are, let's say, 2-dimensional, but with a 3rd dimension added. And while Street Fighter, it's strictly 2-dimensional. And one key point is that, as you saw, the environment surrounding these characters changes quite a lot depending on the point of view of the camera. And this, since what we are using to train our agent is a great part of this information is related with the frame, the fact that the scenario is changing, it's really hard, makes the problem not so easy to tackle. And so yes, of course, the fact that the scenario is changing is somehow something complex to manage for the reinforcement learning agent. But of course, you know, if we as humans are able to do that, we believe that the algorithm should be able to do the same thing. Not sure if I got your question correctly, Rockerman, let me know. In the meantime, Lord Morgul is saying that Eddie and Warang are more easy to play with respect to, for example, King and Kunimitsu. You're totally right. That's the reason why I usually used Eddie. That was pretty easy to use. And as Lord Morgul is saying, it depends on the type of moveset and typical fight, long or mid-range or close range, and that's completely correct. This is the reason why I wanted to test the same characters on, let's say, random part as and take it as a reference, and then train the same set of characters and try to train an algorithm with them. Now, Marco, this is another interesting question from Marco. He's asking, is one action not bringing damages to the opponent signed with a penalty? Currently, this is not the case. I experimented this idea a little bit in training my own algorithm, but currently I'm not using it. Of course, it's a way to embed some knowledge, some human knowledge in it, because, you know, if you are not hitting someone, it means that your action was not optimal, and that's a good idea. It needs some research, meaning that you have to experiment with it and see if your training will improve or not. Rockerman, thank you. Okay, I got your question right. Andrea Seed is replying to Lord Morgul, and so that's great. Now, today we revealed this 3rd game. I showed you the random agent performance. I will try to do my own performance, and we'll see. I will be more or less on the same level, so pretty bad. I can anticipate you that on Thursday we are gonna see the 4th game, and we will complete the first set of games we interfaced for this first revision of DIAMBRA. Then next week, starting on Tuesday, so 1 week from now, I will be finally showing you our trained agents. So the first one on Tuesday and the second one on Thursday next week. The first one in Dead or Alive and the second one in Street Fighter. I will show you the level of performance they have, level of reward during training. I will tell you about which algorithm I used, and we will see how good they were able to become. Now, I really hope it will be fun. I am more or less sure about it. We will be watching at someone playing, basically an algorithm playing by itself, and we'll see if they will be able to let's say move from the first stages up to the last ones. It will be super interesting, and maybe we will be also able to fight against them. So basically in AI versus human condition. Now let's move on, and let me try to face the computer myself. So this means that instead of AI versus com, we have AI versus human versus com, and so it's myself. Now this is just to let you know who is playing against the computer, and this will be useful with, not now maybe, that you are able to see that you are looking at a random agent, but when we will have reinforcement learning ones, it will be different. I am almost sure. So let me see. Let me try to face this one. Okay, so standard window layout, configuration. Hopefully it will be okay. As I told you, this game is kind of a little bit buggy, but it seems to be working. Now, as usual, here on the left, this image is freezed, but it will be updated pretty soon. Now I do have to select my characters. I will select the same ones that we already used with the random agent. Now I said I am pretty bad, so let's see what I can do, but I believe I won't be so good. Yeah. Now this guy is also one of the characters with the highest health, so it's hard to fight against. Come on. If you have something, I doubt I will be able to learn something about this. Okay, now. Now, Andrea, I believe that you can be a good opponent. So to fight against the AI, and so please keep in mind that you can always fight against it here with me. I don't even know any combo at this game, so I'm trying to playing with common sense. Let me play with Yoshimitsu a little bit. Let me see. Yeah, I love this, when he stands up on the sword, it's kind of strange, so let me see. Nah. Okay, now first one bad, really bad, minus 3.18. Let me see again. Minus 3.18, so even worse than the random agent. Great. Let's see. No. Yeah. Now they also use this kind of couple moves together with the other characters they are using, like in combo. I don't know how to do that at all. Okay, I'm done. Kurara is saying, change your neuron connections weights. You're right. Perhaps I do have to change my neurons completely, maybe. That can be a good idea. I don't think, I mean, Lord Morgul is saying that it can be also a problem of the interface with the gamepad, but I don't think so. I mean, it's just that I don't know the game. For example, with the other life that I know it a little bit more, I'm pretty good also with this gamepad, and I mean I'm able to reach at least 4th or 5th stage. So in this case, I just don't know the game, but you know. So in this case, you know, in this case, you can see that the random agent is even better with respect to the human player, meaning that using human experience, if the human experience is collected by from me, is not a good idea. So of course, in order to do that, you do have to find the good data set collected by good players, good humans. And so that is something that usually is not available. And that's the problem, typical problem of having human experience to be used in pre-training your system. That's a good point, you know, a good problem. Now let me just end this. This is the 3rd episode. We will see how my average performance. Bam, bam, bam. It's not so good, you know. You go Yoshimitsu. Bam. Now the point here is that you and your round ends when you kill one of the opponent's characters. You don't need to kill them all, but just one is enough. So you see here. Now Lord Morgul is asking something. I will let you finish the question. Let me try just to finish this. Oh, come on. Not even a single stage passed. Okay, so yes, we started talking about that type of games. Yeah, as I told you, the key point is evaluating how complex is the observation space and also the action space. So you need to understand what's the computational power required to tackle those type of games, because you know this is something I will share with you in the next week. The power I'm using, it's by choice mainly, but also by constraints. It's limited, meaning that I'm using a standard workstation with a standard GPU, because the idea here is to push the limit toward using something and try to understand how to train something using limited computational power. So in my case, I will be sharing with you my trained agent, and it is based on training performed only in my workstation, not in a cluster. And so the results are of course even of more value, since we are not using huge computational power. We are only using a standard workstation that has typical limitation in this sense. Now let me see if I'm able. Oh, come on. No. Okay. Third round. And this one is also gone, I believe. Let me see. Yeah. Okay, so let's see. Oh, do I have another one? I think so. Oh, last one, I think. Let's see. I will get back to you, Lord, afterwards. I see where you're headed. No, I know. I will never overcome stage number 1. I know. Now, last round, I think. Remember, random agent average performance was minus 2.72. Let's see what's mine. Okay, so now I believe you got why I tried. I focused my efforts in training our RL algorithm to play these kind of games. As you can see, I believe I have more chances in being able to train an RL algorithm with respect to understand how to play these games. So for me, that's the best solution in terms of possibilities of good outcome. Now let me just select this. This is done. I believe I just have to move to the fighting section, and that's it. Okay, so minus 2.56. So I am better than the random player after all, even only by like 0.2 points. That's it. And so yes, let's say these are two baselines that we can compare with an RL algorithm. Okay, so I believe that now more or less everything that I wanted to share with you is here. As I was saying, in 2 days, so next Thursday, I will be presenting the fourth and last game we interfaced with DIAMBRA. I will be then next week presenting you RL agents trained in the first 2 games. I will share with you techniques and what's behind the scenes in that training. Hopefully it will be fun to watch. I believe that for today we are more or less done. Let me say that I would like, if you are able to, spread the word. I would like to invite you to follow us on all our channels. You can find them on our website. Follow our Twitch channel, and in this way we will be able to provide you really fun tournaments in the coming year. We are already talking with a lot of interested and interesting people willing to take part in these tournaments, training their own agent and fighting one against the other to finally win the competition. I believe it's enough for today. I want to ask you if you have any final questions about what we saw, and if you have any additional comments, please don't hesitate to share them through the chat. In the meantime, I really thank you all for being here also today. A final reminder: if you want to see additional games interfaced, like typical classic, let's say retro games like these ones, on the website there is a dedicated form. You can find it here, for example, where you can suggest new games and new modes that you may be interested in watching them. Thank you, Lord, for your references. We will take a look at it. As you can imagine, interfacing new games requires effort, and so of course it is also a matter of how interest is in that specific development. Curaro is asking, how much time does a random agent have to be trained to pass at least stage 1 based on your current computational power? Okay, let's say that it's hard. Let me remind you one specific thing, that moving and, let's say, progressing through the stages is less informative from the point of view of how good a trained agent is less informative with respect to the average reward. This is because, for example, in Dead or Alive, the highest possible reward is obtained when you reach the final stage, and also the lowest possible reward is obtained when you reach the final stage. Now the reinforcement that the random agent in the other life was able to reach stage 2, stage 3. I can say that more or less 1 month of continuous training is needed to see a very good agent playing. I will share with you more details about this in the next live, when I will show you all steps and also all performances through the final, let's say, configuration of the agent that it will be reached. Rockerman is like questioning my abilities in Tekken, and that's pretty sure. So this is, again, this is the reason why I turned my back into playing, and while, let's say, giving the possible chance to reinforcement learning. In Tekken, I don't know. I have not trained an agent in Tekken so far, but I will in the coming weeks. I will let you know. I will present you results, of course. I can say that based on my previous experiences with the other games, more or less 1 or 2 months. For the first stage, I believe that 2 weeks maybe of continuous training can be. Andrea is offering a free Tekken course. Not sure I need it, since I have my RL agent soon. I will have it. Thank you, Curaro, for being here. It's always a pleasure to have you. And so, guys, I believe that for today is enough, and okay, thank you for joining me in this new live. For those of you who are available, I will see you on Thursday for the 4th game. It will be interesting too. I can assure you it will be one classic again, as in these first 3 episodes. It will be fun. it will be even more complex from the random agent point of view. You will see it, and also from my point of view. I will be basically hopeless also in that game. And so for those interested, please join me on Thursday, same time, 10 p.m. Italian time. Again, guys, thank you, and enjoy your night. See you next time.